Hello, everybody. Welcome to today's presentation from Makino titled Maximizing the Benefits of On-Machine Measurement. I'm David Lyle, Associate Editor with Modern Machine Shop. Today, we have a great presentation from our friends at Makino and a little bit about it. On-machine measurement systems can reduce machine tool setup time, prevent spindle crashes, and optimize tool settings. Not all shops know the secrets to maximizing the benefits, so we're going to talk about that today. On our agenda, we're going to learn why machine accuracy matters when implementing on-machine measuring. We're going to talk about identifying the most beneficial types of measurements performed on machine tools. We're going to discover the multiple advantages of on-machine measurement and understand how to implement and simplify macros. Here with us today is Paul Meredith. He is a metrology support team leader for Makino. He began his career in the machine tool industry over 15 years ago by leveraging his extensive knowledge of electronics. He helps Makino's customers benefit from online measurement systems with machine tools. And over the last 10 years, Paul has contributed to Makino's R&D efforts and utilized his passion for technical instruction by training numerous customers and service engineers. A little about our presentation here today. If you have any questions during the presentation, we highly encourage you to use the Q&A and the chat section over on the right side of your screen. You can submit a question there, and we will do our very best to get to it. I also want to remind you that this webinar is being recorded and will be available on our website, mmsonline.com. You'll also notice that we have some handouts. If you click on the handouts tab over there, and I'm sure Paul will mention this later on as well, there's a few PDFs that you can download over there. So again, please submit questions as they come to mind. You don't have to wait to the end or anything like that. Just send them on over there and we'll do our best to get to all of them. So for now, I encourage you to sit back and relax and enjoy this presentation. And with that, I hand this over to Paul.
All right, thanks, David. So going ahead and getting started in this, what we will be kind of covering today, just and as the overview is, it's all on machine measurement systems, probing and tool measurement specifically. So we'll go over some information on those, a bit about macros, some of the uses for probing and tool measurement, and what kind of things, just a brief slide on what we might see in the future with this. So before we really get rolling, we have a little bit of a poll that we're going to go ahead and present, where you can just kind of click on the types of things that you use currently in your shop or what you might be interested in, and give us a little bit of information on your background and the things that you're looking for information on. So getting started with everything, we're going to start with some probing. What is a work measurement probe? So a probe is basically just a high precision switch. So it's a switch that will repeat to a very, very accurate level. When the probe stylus touches an object, it sends a signal back to the machine tool control. That signal tells the machine to stop and to record the position at which that switch was triggered. That signal can be transmitted via wire, or there's a wireless transmission protocol that's used for a majority of milling machine probing. The communication in a milling machine is typically wireless. There are two different types of communication. You have infrared light, which they'll call optical probes, or there are radio frequency, which normally are just called radio probes. These optical and radio signal transmissions provide convenience because there's no wire to deal with, but they also add a bit of cost. However, these are kind of the standard probes for milling machines. The receiver that's used, whether it's an optical or a radio, is common to the work probe, and it can be common to the tool measurement system. So if you wanted to buy some kind of combination of probe and a tool measurement device for your particular machine, it makes it slightly easier to implement because you have both devices that can communicate with one receiver inside of your machine. There are wired probes available. Typically, these are installed in a fixed position or manually inserted into the machine. They're usually used on turning machines, however, they can be used on mills. The biggest problem is you can't really put them in through a tool changer because you have this wire attached to the probe. So that's why the wireless probes tend to be used in milling machines. So they're the least expensive of the NC communicating probes, but they're also the least convenient, again, because you have to deal with the wire. And then there are also manual types of probes that don't actually communicate with the machine tool control. Ordinarily, they just light up when they contact a part. So you'd use it kind of like an edge finder, somewhat expensive edge finder. They work, but you can't automate them like you can with a machine tool probe. As far as the two types of radio probes and the two types of probes and the communication protocols, optical and radio. I get asked fairly regularly which one is better. In essence, radio is better. You have a longer range. There's no need for line of sight, so you can mount the receiver anywhere in the machine. It doesn't have to be in the machine envelope. It can be on top of the machine, near the control, near the machine tool cabinet, whatever it might be. And there's no worry of cleanliness impacting the communication signal. So with an optical probe, you have this probe in your machine, in your tool magazine. It's getting coolant dripped on it. It's getting chips thrown on it. And then the receiver tends to be in the work envelope also. So they're constantly getting dirty and pelted with things. And if they get dirty enough, you start to lose communications. The advantage that optical has is it's less expensive, a bit less expensive, and it may be required in a facility with a strict RF policy. There are certain facilities where they just are not allowed to use any kind of radio frequency communications protocols in the building. So in a situation like that, you'd be stuck with optical. As far as the probe's accuracy, I talked about them being just very accurate or very precision switches. A standard probe will repeat to a micron or less. So you can touch off on the same point over and over, and it will record that point over and over to within a micron. You can also purchase higher accuracy probes. The higher accuracy probes will repeat to a quarter to a third of a micron. You just end up paying a little more for the extra accuracy on those particular probes. Along with the probe accuracy is machine accuracy. The machine accuracy is just as important as the measurement system accuracy. A high accuracy probe on a low accuracy machine will not give high accuracy results. You're stuck with your least common denominator. So if you have this probe that'll repeat to a third of a micron, and your machine is worn out, has sloppy ball screws, whatever it might be, you're just not going to get that good of a result with it. So the more accurate and repeatable your machine, the better your results will be. Part of the testing that I've done on the systems for our machines is on one of our A61NX machines, which is a horizontal machining center, 4-axis. I did a test where I was doing 100 x-axis position checks with tool changes between. So I would have a tool in the spindle. I would send that spindle into a program where it would just run around the machine. It's running the spindle. It would do that for about a minute, and then it would tool change the probe into the spindle. That probe would then come in and measure a feature on a part that was mounted on the fixture. And in that 100 check routine, my variation in that x-axis position was only 1.2 microns of total variance. This is on a machine that does not have scales. It's just using pulse coders for its positioning. The spindle was running, so the thermal compensation was doing what it should have been doing. But it's just an example of you need a good machine in order to get good good measurements out of a system like this. So why would you use a probe in the first place? Well, reducing setup time. So you can use a probe to automate your part location in the machine. If you're a job shop, if you have variations in your blanks, in your billets, in your castings, whatever it might be, you don't have to spend the time bringing an indicator, an edge finder, or whatever it is into the spindle to figure out where the part is in the machine. You can run this program that will come in and find that part in space in seconds as opposed to minutes. It can reduce scrap. So whether the part is loaded properly in the first place, whether the proper part is loaded, you have a couple of different parts that look very similar, but one has a feature in it that the other one doesn't, and the operator may load the wrong part. The probe can come in and check to see if that particular feature is there before it ever even runs that particular part. Come in, do a quick one-hit check, verify that the correct part is there, and then go ahead with the program. So it reduces scrap, it reduces the chance of human error, and it increases spindle utilization. As I was saying before, if you're sitting there with an edge finder or a manual probe or a 3D indicator or whatever it might be, you're wasting time. That spindle is not cutting chips for you, and it's not making you money on the machine. So you're essentially paying for speed and you're paying for safety because of the checks that you can do on those particular parts. So what can you measure? So on this, I actually have a video that I want to play. This video is a video I recorded in one of our A61NX machines. So this is bringing a probe into the spindle, turn the spindle on, and then I'm coming in and measuring the Z height of this block. Then I'm coming in and finding the bottom of the pocket to make sure that it was machined. And then it's running a 5-point rectangle pocket measurement routine. So in that quick routine, probe is back off, and now it's back out of the spindle. In that routine, and I can play it again here while I'm talking, I was able to find the top of the block. I was able to find the bottom of the block, verify that it was cut to depth, and then I was able to determine the width of that pocket, the height of the pocket, the center of it, and the orientation of it. So if this pocket was loaded or this block was loaded in the machine, maybe it was slightly off. Maybe whoever put the fixture in or the vise in didn't quite line it up properly. I could also use that exact same routine that I just ran to do a G68 coordinate system rotation to verify that the pocket was loaded in there or the block was loaded in there properly. So those are some of the routines you can run. You can check for surface locations. You can find X, Y, or Z locations. You can find corners of your workpiece, slots, ribs, bores, bosses. You can find the centers of them. You can find the widths, diameters, distances between features. So if you have a bolt hole pattern and you want to make sure that the correct pattern was loaded in, you can measure those. So it ends up being kind of up to your imagination, all of the things that you can or decide on measuring. There's also safety and automation requirements or opportunities. So is the part loaded properly? Is it flat in the fixture? Is if you're on a 4-axis machine, is that 4th axis oriented properly toward the spindle? If you have a multi-part fixture, if you have we have a lot of customers who will nest 40 parts on one fixture. Well, they don't always have 40 parts that they're running at a time, so they may only end up running 15 of those parts. Well, if the program's going to keep going and do all 40 of them, then that's a huge waste of cycle time. So they can actually have the probe come in and verify how many parts are in the fixture before they ever run it. And that way the program will automatically run just those 15 parts or whatever it might be. If your castings have a lot of variance, maybe the casting has shifted a little bit. You want to make sure if your parts or your programs are just dialed in perfectly to one size of casting, well, if that shifts, that can cause problems. You can, run the tool into the part, whatever it might be. So you can verify that that's correct, and you can do prior operation check. You can make sure that if you're going to bring in a tap to come in and tap some holes, you can take that probe and send it in to verify that all those holes were drilled first if you need to, just as an example. And then there are post-machining checks, so critical feature measurements. So you can come in and verify that you have a boring bar to get a very precision bore in a part. Maybe it's a new insert in the boring bar. So you can have the probe come in and verify that it actually machined to the dimension that it needs before sending that part back out of the machine. You can make sure that slots or ribs or whatever it might be are the correct dimensions. And you can verify that the proper tool was used or that it's not too worn out. Maybe it didn't cut enough material. So you can have the probe come in and verify things like that. So these are all things that you can do with the probe, in addition to checks for the machine itself. So you can do things like center of rotation checks. There are programs and macros available that will verify all of your rotary axes, make sure that your rotary axes are aligned, that the centers are documented properly so that any 5-axis parts are in space as they're supposed to be. You can check for axis wear, you can check machine and fixture alignment checks. You can, again, if you have a 4-axis machine, somebody puts the fixture in and it's not quite oriented properly in B, you can actually, there's a quick check you can run where it will automatically reorient that so your fixture is parallel to your X or Y axis. Now, why would you not want to use a probe for something like any of this? The biggest reason, you have expense in buying a probe and fitting it to your machine, and cycle time. There are, if you're a production shop, your fixtures, your castings, everything is exactly the same all the time. You're going to take up cycle time by running probe checks. It may only be 15, 20 seconds to tool change a probe in, start it, come and take a couple of hits on a part and come back out. But 15 or 20 seconds per part, in some shops, that's not acceptable. In a lot of shops, if you're doing die mold work, especially, they can be very, very critical checks. They can be very useful. They can save you a lot of money. So moving on to tool measurement. So tool measurement systems are devices used to determine tool dimensions. You have contact type and non-contact type. The signal, again, can be transmitted wired or wirelessly, and the devices typically repeat to about a micron on average. So contact type measurement devices, you have a high precision switch, just like a probe would use, with a high hardness stylus. The machine touches the tool to the stylus to measure length and diameter or broken tool status. They are less expensive than non-contact options, but you're also limited on the measurements that you can do with those particular tools, and they are not ideal for fragile tools. So if you have a PCD tool, you wouldn't want to bring it in and touch it off of a hardened steel stylus on the on that measurement system. So the wired versions are less expensive on these contact type measurements, but they're a little more difficult to install just because you have to run the wires through the machine, keep them out of the way of any chips or coolant or whatever it might be. The wireless versions are very convenient in that they use the same receivers as the wireless probes. Only one receiver is needed per machine. So you can have one single receiver and it will run both a work measurement probe and a tool measurement device. The wireless units are very easy to install because there are no wires. There's just a battery that goes into it and it just gets mounted somewhere on the table or on a bracket next to the table, whatever it might be. If you have a machine that's limited in workspace, you can actually remove it if you need to. You'll need to recalibrate it when you put it back in, but it's pretty simple to do. Non-contact tool measurement devices ordinarily are a laser-based system. The machine moves the tool into a laser beam. You have far more measurement options than you do with the contact type units, but there are not wireless units available for something like that. The non-contact systems are available in fixed width or separate systems. So the fixed width systems, typically I see those on vertical machining centers. They will be mounted to the table somewhere off the edge of the table, and the distance between the laser heads is a fixed distance. Ordinarily, it's just a little bit larger than the largest allowable diameter tool for that type of machine. The fixed systems are easier to install than the separate systems because the separate systems require custom mounting but can be tailored to each machine. So like on this previous slide, this particular installation is on one of our horizontal machining centers. This is an A51NX, and this is a separate system that is an angled beam system, but everything is out of reach of the spindle or the tool. So there's zero risk of a tool contacting any of that at any time because it's all out of the machining area. So it's a little bit safer, more difficult of a configuration, more difficult of an installation, but it's very, very effective for what people might need to do. As with the work probes, machine accuracy is just as important as measurement system accuracy. Again, high accuracy tool with a low accuracy machine will not give good results. On the A51NX machine that I showed earlier, I had 250 measurements in one of the tests that I was running. I had a 1/2 inch end mill, about 6 inches in length, and I did 250 different measurements, moving the machine around between measurements, running the spindle continuously, and over those 250 measurements, I was able to repeat to 2.8 microns that was the variation over the entire test. So again, no scales on the machine. It uses the pulse coders for positioning. You need a high accuracy machine to get good measurements from one of these systems. So what can you measure? I have a couple more videos to show here. So the first one is, it will load. The first one is showing bringing this tool over and taking a measurement with the laser. So it brings the laser up to the tool. It's doing length first, and you'll see it move over to the side just a bit, and then it's doing a radius or diameter check. This one's doing a double-sided check, where it actually goes on the top side and bottom side of the laser. And once it finishes that particular check, then it will go in for the cutting procedure on that particular part. So we can do on contact and non-contact systems. We can measure length, diameter, and broken tool status. So that will work whether you're doing contact or non-contact. With the non-contact, you add in a lot more measurements that you can take. You can come in and find your corner radius, number of flutes, cutting edge and run out checks, slitting saw width. If you're using some kind of saw, you can measure top and bottom of it. Back cutting height. If you're trying to do some kind of O-ring groove where you're coming into a part and then trying to bring the cut back on the backside of the part, you can actually measure something like that. And then you can do custom tools with multiple features. If you have some kind of combination drill and reamer or a port tool or something where you have multiple heights on the particular tool you're measuring, you can measure all of the heights on that tool. So why would you use the system? Accurate measurements without a presetter. You don't have to worry about mistyped tool data. So even if you have a very accurate presetter in your tool room, you have that little sticker and have to have somebody enter in that data. Somebody fat fingers a number, and that can cause a big problem in the machine. If it's measuring it in the machine, there's no data to type. You have automatic tool wear compensation. So as a tool starts to wear, you can determine, what the true length is. You can do safety checks on it. So you can verify is the proper tool in the spindle. Did the drill break? Is the tool actually an end mill or a drill, or is it some kind of inserted tool? So there are a lot of safety checks that you can do on them as well. One of the other systems or checks that you can do is a broken tool check. This is that same tool that I was just showing. So it comes in and does just a quick pocketing routine or whatever it might be. And then after it finishes, it will send it over and just do a quick check in the laser just to make sure that it isn't broken off or it's not pulled out of the holder and it's too long. Once it verifies that that check is complete, then the tool changes out and we're all set. So the next thing is macros. Macros are what scares everybody about these type of systems, because you look at a macro program and there's a lot of stuff in there that people don't understand. But a macro can describe one of several things. So a macro variable is a location of storage in the machine control for some kind of numerical value. So most machines have 100 or a few hundred macro variable storage locations that are available. A macro can describe the program language that is utilizing those storage locations. It can describe a program or programs written using those above items. They are also commonly referred to as macro software or routines. So anything written in this case, or the case of the of Makino machines, we have FANUC controls. So anything written using FANUC macro B programming language is considered a macro program of some sort. So the macro programs are what make measurement systems more than just expensive switches. They tell the machine how to move, how to take the measurement, and what to do with that information afterwards. These programs use the control skip signal to determine the exact positions the machines were in when the device was triggered. So the probe or the tool measurement system was triggered. And that's how it calculates where in the machine things are. The macros can be custom written for your application. They can be supplied by the machine manufacturer, or you can purchase macro packages from various sources. So Makino has our own macros that are available. We also use some of the measurement system manufacturers' macros in some of our systems. You can purchase macros from specialty programming businesses. So you may have someone that you work with regularly who works with macro programs. You may have someone who works for you who custom writes macro programs. Once you understand how they work, they're not too complicated, but there's still a lot to them. The macro packages may include dozens of programs. Some of those programs may have thousands of lines of code. The different programs do different things, but typically you have a calibration routine, several different measurement routines. You have a parameters program, you have a bunch of safety programs, you have power on and off. So there are quite a few different programs involved in it, and they all just do different things. A lot of the off-the-shelf packages are very complicated just because of safety, verifying that everything is exactly as it should be as it's running. So it's trying to prevent you from damaging your machine or damaging the measurement equipment itself. So because macros are complicated, how can you simplify them? The biggest thing that's always been available: classes, books, and education. There are classes that you can take. You can take them from the machine tool manufacturer, from the measuring device manufacturer, from the machine control manufacturer. There are hundreds of books out there talking about macros and how they work. There is a lot of information available. In recent times, as controls have gotten more powerful, we have a lot of GUIs, graphical user interfaces. So some of the screenshots you've seen throughout this presentation are from Makino's Pro 6 control, where there are user interfaces where you can go in and just click a button and tell it what type of measurement you want on the machine. Then the machine will automatically go ahead and take that measurement and populate the location you're looking for with the measurement value you want. There are apps available. So most of or all of the measuring system manufacturers have apps for your cell phone that you can download, and it will guide you through finding the correct coding to type in for your spindle probe, your tool setter, whatever it might be. And then there are software packages available also. So you can get offline programmers, you can get offline GUI interface software. There are a lot more resources available now than there used to be. And then the last thing that I kind of wanted to mention is what's next? Where might we go with these measuring systems? As technology advances, you look at PCs and how advanced they've become. You look at the smartphone. 15 years ago, the smartphone was awful. And now they're more powerful than computers were 15 years ago. So you have advanced processing power. As they're putting more and more powerful processors in machine tools all the time. You have high resolution CMOS imaging. So the imaging sensors that you have in digital cameras and phones, whatever it might be, those can be used for a lot. We have a system in a lot of our machines called Vision Broken Tool. And if you look at the very bottom of this slide, you can see kind of a shadow of a drill. This is an image that the Vision Broken Tool sensor took of a drill, and it's able to use that image and count pixels in that image to determine how long that tool is. And we can determine whether or not that tool is broken or pulled out or whatever it might be. As the CMOS sensors get more and more powerful, it means we can do more and more with them. We may be able to give an accurate measurement on a tool down to microns. We may be able to find where a workpiece is inside of the machine within a very, very small window. There's laser scanning opportunities. You may be able to have some kind of laser scanner that'll come in and scan the entire work envelope and populate something like a collision safeguard system where it knows where everything is and it will not allow the machine to wrap it into a position where it would strike something in the machine. Material advances make things lighter, faster, stronger. And then you have AI learning and prediction stuff. As AI picks up, it may scan your code in your program and say, oh, okay, well, this is a drilling routine, and this next tool that came in, it's going to some of those same locations, so it's probably tapping. Maybe I should verify that that drill isn't broken before I send that tap in screaming down into a hole to do a tapping operation. So it's just kind of this slide, I guess, is just to kind of get your ideas going and get you thinking about, what may come, what might I be able to do in the future on the machine. So that was kind of a rapid fire presentation, I think, trying to cram quite a bit of information into a short time. But for any other information you might have, you can visit makino.com. Or if you want to contact webmaster at makino.com, we can get you some further information on our machines or any of the information that I've talked about today. With that, I'm going to send it back to David, and I think we're going to get into a little bit of question and answer here.
That's right. I appreciate the presentation. That was very helpful. Before we transition to the question and answer session, I just want to remind everybody that this webinar has been recorded and that there are handouts there available to you if you click over on the handouts tab on the right side of your screen. We still have time to field questions. I have several here that I'm going to addressed to Paul here, but please submit more if you have them. So looking at these questions, can you tell me about the relationship of trusting how you're measuring a part, and can you measure it with the same machine that's making it? Like, is that relationship one that can really be trusted, or do we have to go outside the machine to do this?
Assuming you have a high accuracy machine, then sure, the device that you're using for the measurement will have had a calibration done using some sort of calibrated artifact where it's able to get a very, very good calibration using this artifact. Are there instances where those numbers could be off? Sure. If you have something that's that critical that where you need a super precise measurement, you'll have to send it to your CMM and get something run through there. But for the most part, yeah, these things are very accurate. There's no bias per se. If you have an accurate machine, you're going to get accurate results.
Okay, can you explain, are there standard routines for probing built into our CNC controls themselves?
So, yes, to a certain extent. A lot of manufacturers will have some sort of user interface where it will be able to call up some of the factory written or macro packages that that manufacturer has purchased in order to run those systems. If you are trying to implement a probe or a laser or a touch tool length sensor in a machine that you are trying to do yourself, I don't think that most of them come with those macros. It's something that you would have to install yourself or acquire yourself, purchase along with those measurement systems. But yeah, if you're buying a machine from the factory or from the manufacturer with a probe or a tool measurement system in them, then yes, all of those routines should be built in when you purchase that machine.
Okay, I have a couple questions that relate to sort of brand of the probe. So Eric had a question: can probes be used on machines other than Makino machines? I mean,
Oh, sure.
Yeah.
Yeah, I mean, you can integrate a probe on pretty much any CNC control that there is. So it doesn't really matter who the manufacturer is. There should be some sort of skip signal input on that machine that will accept a probe input. You would then purchase the proper macro programs to run that probe on that machine. But just about any machine out there that I've seen, you can implement a probe or a tool measurement system on.
All right. One question from Mr. Rodriguez: can a probe and its macro be used to check spindle health?
I suppose there would be, you could check runout maybe with it.
Okay.
Other than that, I honestly can't think of a good use or a good way to do it using the probe. Most of the time, spindles, at least our spindles, if somebody is having a spindle issue, it's usually related to it's just worn out. They've had some unintentional contacts, or they've just beaten the tar out of the thing. Maybe they've beaten up the taper a little bit or something like that.
Right.
So it tends to be bearings or it tends to be the taper itself. The taper you might be able to find with a probe if you did some kind of orientation routine where you're orienting the probe at 4 90-degree increments and trying to measure something. But the bearings, I'm not sure how you would be able to determine that with a probe.
Okay. Question from Mr. Hansen. Essentially, can you export the measurements? Where's the data go?
Sure. So good question. There are so the data gets stored in macro variables. So I mentioned you have all these storage locations where you have where you can store numbers, is what macro variable locations are. So when you take a measurement with the probe, that measurement can get output to wherever you want it. So in your program, you would just say, essentially store the result for that particular measurement in variable 601 or 602 or whatever it is. And once you start to fill up those variables, every control that we have, I would imagine most controls on the market have a macro variable file output, where that file can be written as a CSV file ordinarily, and it can be output either over your network or via USB drive, wherever it might need to go, and then you can manipulate or analyze the data at that point.
Okay. So looking at sort of potential drawbacks, we had a question. Cycle time increase is a major drawback to any solution. And then kind of related to it, how do I decide if it makes sense to spend time on the machine tool measuring a dimension versus making a part?
That's the drawback to any of these systems is it consumes cycle time. If, as I kind of was mentioning with the probing, if you are a production shop, you're trying to get every millisecond you can out of every single cycle. There are quite a few times where it doesn't make sense to operate a system like one of these, because they do consume cycle time. It depends on how critical your parts are, how critical your tools are, how variable the process is. Is there a chance that something is loaded properly or improperly in the machine? Is there a chance that the operator put the wrong tool in the wrong location? It's kind of a risk-reward analysis. And it's up to you and your shop whether or not you're willing to spend that cycle time to do these measurements. In a die mold shop, I would recommend these all day. The blending that you can get by being able to get tools perfectly measured to each other, the amount of time that you can save on finishing the parts is huge. So definitely in a situation like that, or if you have critical parts, if you have expensive parts, if you have operators that you don't always trust to put things in the right place, those are situations where the cycle time tends to be worth the risk.
Very cool. Okay, a question from Steven. He says, you mentioned measuring variances in castings. Is the programming at a place where tool paths can be scaled based on a casting being over or undersized from nominal dimensions?
Theoretically, you can do that. There are functions in the control where you can do program scaling. More than likely, what people end up doing, from what I've seen, is there will be essentially go-to lines in their program where the program is written for the largest part that they've seen.
Okay.
And if the casting that they receive is smaller, then they will end up bringing it in closer to start. So they'll end up skipping a couple of lines where on a smaller casting, it would just be cutting air.
Okay.
That tends to be what I see most often.
All right, looking through some questions here. Okay, so this is kind of a similar question, but kind of from a different angle. Are there possibilities to use your measuring data for compensating your tools? For example, when milling a critical hole, measure it and finish it in an automated cycle.
So there are a few people I've seen who do things like that, where they will come in, fairly sure that it's going to be undersized on first check. So they'll measure what it is. They will adjust their boring bar, whatever it might be, and come to do it again. There's been some experimenting that we've done with systems that have essentially adjustable cutter dimensions. So you can send a signal where it can adjust that cutter dimension on the fly, and you're doing closed loop type compensation on the part. So I can't remember. I can't remember which of the things I'm actually allowed to talk about. Sure. So I don't know if I want to go much beyond that right now. But yeah, closed loop machining is a thing where you can immediately take a measurement, make an adjustment, come in and get the number you're looking for.
Very good. It's an exciting field. I mean, and this is, these are tools that can improve anybody's workflow in certain situations. Is there anything else, Paul, that you wanted to share with everyone before I close this out today?
I think I've covered most things. If there are further questions, you can get a hold of me through the webmaster@makino.com address, and I'll try to help you out the best I can.
Perfect. All right, and with that, we're going to wrap this up. But make sure that you download those handouts that are available on the right side of your screen under the Handouts tab. And also, this presentation will come to your email. You'll receive an email later on that will provide you a link to the recorded webinar. If that fails, we have webinar archives on mmsonline.com. I encourage you to get in touch with Paul if you have any questions regarding this presentation. And I want to thank everybody for joining us today. And with that, have a great rest of your day, and we'll see you next time.